Welcome back. Today we'll discuss problems on boundary conditions between dielectric interfaces, and also we will do the problems on applications of Poisson's and Laplace equations. Okay, so we will start with two problems today. The first problem will be on the boundary conditions. See, the question states that there are two extensive homogeneous isotropic dielectrics which meet on plane z is equal to 0. For z is greater than 0, epsilon r is equal to 4, and for z is less than 0, epsilon r1 is equal to 3. And there is a uniform field of E1, this is a uniform field, exists for z is greater than 0. And yeah, 1 minute, I think this is 2, right? You take it as 2, okay. And this is E1 for exists for z is greater than 0. Find E2 for this material and the angles which they make with the interface and the energy densities and energy within the cube. If you see the problem, it can be clearly understood that there is a dielectric interface. This is one dielectric medium. This is z is equal to 0, and this is another dielectric medium, which is this is medium 1 entirely, which is having an epsilon r1 value of 4, and this is medium 2 with epsilon r2 value of 3. Right, this is z is greater than 0, and this is z is less than 0. Okay, so which means that this is the right, this is z is equal to plus infinity and z is equal to minus infinity, and this is z is equal to 0. So this means the materials are placed in this way, and there is an E1 field which has been mentioned for us, and he wants to determine what is the value of E2. So in this case, what we should do, we should employ these boundary conditions to determine the fields when field in one dielectric medium has been given for us. So in that case, when we start doing these things, let's have a quick recap of dielectric boundary conditions. When I start with the dielectric boundary conditions, as already mentioned, when I do have two medium, this is medium number 1 and this is medium number 2. Let us suppose this is E1 and this is E2, and this is medium 1 and this is medium 2. So what are the dielectric conditions which I do have? The first dielectric condition is ET1 is equal to ET2. Second is dN1 is equal to dN2. And the third one is epsilon 1 cot alpha 1, okay, is equal to epsilon R2 cot alpha 2, right? Or this can be simplified in this fashion, which we have already discussed. If I substitute, because I know that D is equal to epsilon naught epsilon R into E, right? This is nothing but permittivity, absolute permittivity. So if I substitute here, what I will get? For the two medium, these things will be different, right? Because epsilon naught is constant. So this is condition number 1, this is condition number 2, and this is condition number 3. I will employ these conditions today for determining the electric fields. So I will start with the first one. See, the field has been given for me. This is epsilon R2. This is R2. The field has been given for me. Electric field E1 is equal to 5AX minus 2AY plus 3AZ, isn't it? See, this is Z is equal to 0, right? So which means that the curve is like this, isn't it? This is Z is equal to minus infinity, and this is Z is equal to, and this is Z is equal to plus infinity, right? So which means that in this one, Z component is normal to this dielectric interface. So which means that this is the normal component. I'll take it as En1. The remaining component is going to be my tangential component. Right. So this is my tangential component and this is my normal component. So I'll write it here. Et1 is equal to 5ax minus 2ay, whereas En1 is equal to 3az. So now I'll employ these boundary conditions. Now the first condition states that Et1 is equal to Et2. So I can easily do it. This is nothing but 5ax minus 2ay. So both are same. The second thing states that this is my second condition, right? So if I want En2, what I should do here? En1 by epsilon r, isn't it? So which means that it is 4 by 3 into 3az. So what I'll get? 4az. So what is my E now? E2. E2 is now, it is Et2 plus En2, which is nothing but my Et2 I have as 5ax minus 2ay, and En2 is my 4az. So this is my E2. The first component is solved now. Now we will move on to the second one now. The angles which they make with the interface. Now I do have E1 component and I do have E2 component, right? So what he is asking is, this is medium 1 and this is medium 2, right? This is E1 and this is E2. This is alpha 1 and alpha 2. He is asking us theta 1 and theta 2. So first let us just determine alpha 1 and alpha 2. Okay, because we know that one particular equation, boundary condition 3, which states that we can employ this equation, or we can directly employ one particular equation, which I will show you. E1 is equal to 5ax minus 2ay plus 3az, right? So which means En1 is equal to, normal component is 3az, right? And Et1 is equal to 5ax minus 2ay, isn't it? Now if you see, this is tangential component, this is E1 vector. So Et1 is normally referred as E1 sine alpha 1. This is referred to as E1 cos alpha 1, right? If I separated these things, if I divide 1 by 1, what I'll get, tan alpha 1 is equal to, what I'll get, 5ax minus 2ay by 3az, isn't it? So we will consider only the magnitudes now. What is the magnitude of this one? This is root 29 and this is 3. This is tan alpha 1. If I do this one, I'll get alpha 1 is equal to tan inverse of root 29 by 3. So whatever the value which you'll be getting, that is your answer. Similarly, for this one, E2 we have already. It is 5ax minus 2ay plus 4az. Here this is the normal component. This is tangential component. So again, if I want tan alpha 2, so this is square root of 5 square plus 2 square by, here I will get 4, right? So this is root 29 by 4. So from here I will get alpha 2 value. So once I get alpha 2 value, so now how to determine theta 1? Theta 1 is very simple. Here you can see it is 90 degrees minus alpha 1, because theta 1 is the angle which is made with the dielectric interface. Alpha 1 is the angle which is made with the axis normal to the dielectric interface. So we need to determine theta 1 and theta 2. So once you compute alpha 1 and alpha 2, better go with theta 1 and theta 2. the calculations to you. This is the way how you do this angles, determination of angles E1 and E2 which make the interface. Now, moving on to the third component now, which says that energy densities in J per meter cube in both dielectrics. We know energy density formula. Energy density is given by half epsilon E square, isn't it? So now I'll compute for E1, which is equal to half epsilon. Epsilon is nothing but epsilon, into E1 square. So this is half epsilon value, you know it. This is 8.85 into 10 to the power of minus 12 into epsilon R1. Yeah, this is 2 actually. Yeah. Epsilon R1 is 4 into E1. You don't write the vector form, you write the magnitude because I want only the magnitude, right? So what is the magnitude of this form for E1? E1 is already known for you, right? It is square root of 5 square plus 2 square plus 3 square whole square. Okay. So what I'll be getting, this is kV per meter, right? So I'll getting into 10 to the power of 3 also here. So this is my energy density. So what I'll be getting, half 8.85 into, this is 9 plus 4, 13, 13 plus 25, it is 38, right? Root 38 whole square, which is nothing but 38 into 4 into 10 to the power of minus 9. So if I calculate it, let me do the calculation in my phone. So when I calculate this particular value, I'll be getting 8.85 into 4 into 38 divided by 2. It is 672.6 into 10 to the power of minus 9 joules per meter cube. Okay, this is my value. Similarly, you can do for eta 2. Eta 2 is half epsilon R2 E2 square. What I'll be getting, half into 8.85 into 10 to the power of minus 12 into 3 into, for this one, what was E2? We had E5ax minus 2ay plus 4az, right? So it was square root of 25 plus 9, plus 4 plus 16, right? Whole square into 10 to the power of 3. So here I'll be getting this value is somewhere around 45, right? 45 into 3, I'll get somewhere around 45 into 3 into 8.85 divided by 2. I'll get somewhere around 597.375 into 10 to the power of minus 9 J per meter cube. This is my expression. Okay. Now we will move on to, I hope now you have understood how to compute the energy densities, right? Now we will move on to the next problem. In the next problem, it states that we are supposed to determine the energy within a cube of side 2 meters centered at 3, 4, minus 5. So we know that this was a dielectric interface and this is Z is greater than 0 and this is Z is less than 0. Right? And he says that here, if you carefully see, it is Z value is minus 5, which means that it is lying in second region, right? This is lying here, somewhere here. So in this region, what is energy density? Energy density will be W2, small w2, and we have already obtained a value there, 597.375. It is 597.375 into 10 to the power of minus 9 J per meter cube. This is energy density, and he wants energy, right? Energy is nothing but integral of energy density into dV, right? So what he is asking? He is asking with a cube of 2 meters, which is centered at this one. So this is the vertex, this is the center, and the side is 2 meters. So how to solve this particular problem, which means that it is a cube the point is somewhere here, and these are the points 3, 4, minus 5. This is the center 3, 4, minus 5, and this length is 2 meters. So how to solve this particular problem? Because we do have energy density is equal to integral of energy density over the entire volume. So if you see that this is the point in a cube, you know that every point is basically equally, every vertex is basically equidistant from the cube. So if this point is 3, 4, minus 5, so automatically these points, x point, he says that it is at 3 at the center, which means that this point will be at, x will be varying from 2 to 4, right? Y will be varying from 3 to 5, whereas this will be varying from minus 4 to minus 6, isn't it? So in this case, I'll do this thing. X is varying from 2 to 4, Y is varying from 3 to 5, and Z is varying from minus 4 to minus 6, and the value is this one, 597.375 into 10 to the power of minus 9 into dv. dv you know, right? It is dx into dy into dz in Cartesian systems. So there is nothing available here. You can do it individually. Separate dx, separate dy, separate dz, because there is no component here. So what I will be getting, 597.375 into 10 to the power of minus 9 into, I will be getting somewhere around 8. So which is something around 4.78 microjoules. This is my answer. I hope now you have understood how to employ boundary conditions for solving electric field problems. Thank you.